Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI-generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will explore the new Olivia Linux cluster. More specifically, we will examine a Fortran program that performs matrix multiplication with OpenMP using the Cray Fortran compiler. I will begin by reviewing information about Olivia on the Sigma 2 documentation pages. I am going to focus on the system architecture and software on Olivia. The Olivia Linux cluster is powered by AMD Turin CPUs. Each node contains 2 CPUs, providing a total of 256 cores per node. With 252 compute nodes, Olivia has a total of 64,512 cores. In comparison, Betsy has about 3 times more cores with 172,032 cores, while Fram, being an old Linux cluster, originally had 32,256 cores, though not all of them are currently functional. The Olivia Linux cluster also includes 76 nodes equipped with the new NVIDIA GH200 superchips. Let us have a look at the Olivia software modules. Olivia is an HPE Cray system that features the Cray programming environment, which provides specialized tools for software development and usage. For more details, you can visit the HPE Cray programming environment webpage. The web address is shown in red. Information about the Cray programming environment is also available on the Lumi documentation webpage. The web address is highlighted in red. In this video, I will use the Cray module system on Olivia. I must first log in to the new Olivia Linux cluster, and I will begin by opening the terminal on my iMac. Then, I will use the SSH command to log into Olivia. Since I have activated two-factor authentication, I need to use a one-time password first. This password is a 6-digit number randomly generated by the authentication app on my iPhone. After entering the one-time password, I then enter my Sigma 2 password. Once logged into Olivia, you'll notice some information displayed in the terminal, including links to user guides and support resources. You can also find additional details about the software available on Olivia. One important note is the new policy regarding the use of Python, R, and Conda. These software tools were originally designed for personal computers rather than Linux cluster environments, and often involve installations with a large number of small files. This can place a strain on the file system when many users install such software, leading to degraded performance of the file system on the Linux cluster. To address this issue, Olivia utilizes HPC container wrappers, which significantly reduce the number of files visible to the file system, improving its performance. After reviewing some of the information displayed upon logging into Olivia, I will clear the terminal before proceeding. I will first list the folders I have created on Olivia. I will navigate into the MXM OpenMP folder, and you'll see how the command prompt changes. We will now explore the module system on Olivia, but first let me clear the terminal. We can explore the module system using the module avail command. Since I will be using the Cray module system, I will load this environment with the module load command. Executing the module avail command again, I get a long list of modules available in the Cray module system. One important module is the Cray Scientific Libraries, which can be loaded as a module. Another notable module is the one for optimizing programs for AMD Turin CPUs. Additionally, a Python module is available, which I will use in upcoming videos. The Cray module system also includes performance monitoring tools. At the end of the output from the module avail command, we can see that the Cray environment is now listed as loaded. After reviewing these modules, I will clear the terminal again. I can use the module list command to view the modules that are loaded by default in my home environment when using the Cray module system. We can see that the default Cray programming environment and the Cray scientific libraries, along with other modules, are loaded. I can save these modules as my new default home environment, so I won't need to load the Cray module system manually the next time I log in to Olivia. Before looking at the Fortran program that performs matrix multiplication, I will clear the terminal. I will first list the contents of my folder. We will start by examining the Fortran program that performs matrix multiplication with OpenMP, and I will open it using the Emacs editor. I will begin by testing the program with a matrix dimension of 32, 7, 68. The first loop in the program initializes the matrices. The matrix multiplication is performed using a triple nested loop. After reviewing the code, I exit the Emacs editor by pressing Ctrl+X followed by Ctrl+C. I have now returned to the command prompt in the terminal. We will now examine the job script used to execute the Fortran program. The script begins by setting the job name and the name of the output file. The script also configures several Slurm variables, requesting one node with one task and 256 threads. On Fram and Betsy, there is no need to request memory usage since you have exclusive access to the nodes, effectively reserving all the memory on them. On Olivia and Saga, other jobs may share the same node alongside your job, so it is necessary to specify how much memory your job will require. It is important not to request excessive memory, as this can impact CPU billing, as explained in video number 3. In this job script, we request 100 gigabytes of memory. This request is not critical since we are already requesting all cores on a single node. Therefore, we could have requested all the memory on the node without affecting the CPU billing. The job script sets the wall time to 1 hour. The file names of the Fortran program and the job script are stored in a variable called file. The job script uses recommended error settings. The module restore system command ensures that modules from the home environment are not carried over to the job. This allows the job script to use modules different from those in your home environment. It is also good practice to avoid having a job script that depends on settings in your home environment. The job script first loads the Cray module system, followed by the Cray programming environment. Although the Cray programming environment is loaded by default when the Cray module system is loaded, it is good practice to explicitly load all the modules required for the job. Since Olivia's CPU cores are of the AMD Turin type, the script optimizes the program's performance by loading the module specific to these CPUs. The script then executes the module list command to display all modules loaded in the job output file. The script proceeds to set some OpenMP variables, including the number of threads, which is matched to the Slurm variable defined earlier. I have also configured the OpenMP affinity to cores and close, as this has been shown to provide the best performance for OpenMP. The script compiles the program using the Cray Fortran compiler. Note that the job script only uses the FOpenMP and O3 options. Unlike the Intel compiler on Fram and Betsy, which required the march or xhost options, the Cray compiler automatically handles CPU-specific optimizations through the AMD Turin module loaded above. The Cray compiler does not support the IPO option, nor does it have the ability to replace the triple nested loop with a highly optimized routine, as the Intel compiler does with the qopt matmul option. As a result of this, the Cray compiler cannot achieve the same performance as the Intel compiler for matrix multiplication using a triple nested loop. Note that the job script uses variables to measure the compilation time. Once the compilation process is complete, the script executes the executable file that was produced during the compilation. Note that the script also includes variables to measure the execution time. The script concludes by echoing some variables to the Slurm output file. I am exiting the job script and returning to the terminal. Before executing the Fortran program, I will clear the terminal. I execute the program by submitting the job script to the Slurm queue system using the sbatch command. We can see that the job is assigned the number 3707. When I check the Slurm queue with the sq command, we can see that the job has finished. Before reviewing the result, I will clear the terminal. I will first list the folder contents, where we can see a job output file. Using the More command, I will open this file. The job output file begins by displaying the list of modules used by the job, and the list is generated by the module list command in the job script. We notice that something is wrong with the execution of the Fortran program, as it finishes in less than 7 milliseconds. On Fram, the same matrix multiplication took about 67 seconds on 32 cores. On Betsy, it took about 40 seconds, and only 32 seconds when using the math kernel library on 128 cores. This suggests that the program is not functioning correctly, as it would be impossible for the Cray Fortran compiler to produce an executable that completes the computation in less than 7 milliseconds. Although the output file indicates that the job exited normally, the very low CPU utilization and memory usage suggest that something is not functioning correctly. In the next video, we will address this issue by using allocatable matrices in the Fortran program. I am looking forward to the next video. Wishing you all happy computing in the meantime.